El Niño is coming, and it's going to wreak havoc on the weather worldwide. We may be facing the most severe weather events in decades. Scientists are concerned about this Super El Niño, then which could strike very soon. Today, we'll take a look at the global impacts and get right to the point. This extreme weather event has been popping up everywhere in recent days. Super El Niño is about to wreak havoc. It sounds dramatic, but what's really behind it? That's exactly what I'm discussing today with a meteorology expert. Dr. Andreas Fink from the Karlsruhe Institute of Technology. His work focuses on tropical weather systems, interactions between the ocean and the atmosphere, and the global consequences of climate phenomena like El Niño. Let me know in the comments if you find these expert interviews interesting, and of course subscribe to the channel if you'd like. It helps more than you think, and it only takes a click. Thank you so much, and now let's get started.
Yes, Professor Fink, so we meet again. We spoke to each other 2 years ago, and I remember back then we were actually in a La Niña phase. Maybe even a beginning La Niña phase. I'm not quite sure anymore. In any case, it was more La Niña instead of El Niño like now, because now the tide is turning, so to speak. You read everywhere about a new El Niño phase. And maybe you can just briefly explain to us what does it even mean, this transition from La Niña to El Niño? What's happening there?
Yes, well, first of all, it's a change in the water temperatures in the tropical Pacific Ocean. It's absolutely huge, stretching more than 10,000 kilometers from east to west. And normally, the warm water is in the west of this tropical ocean, so near Australia, near Indonesia, and cold water, quite cold water off the coast of South America. So the countries of Ecuador and Peru should be mentioned there. And connected with this pattern of sea surface temperatures, there's also a wind system. The winds there usually blow from the east, from South America towards the west, towards Australia, Indonesia, and push this warm water bubble constantly towards that continent as well. And sometimes these winds are stronger than the cold water. We call it upwelling off South America is stronger. So this water is even colder than usual. And this warm water area, it's then pushed even more towards Australia, pushed and is also a bit warmer. That is La Niña. We also call it the cold sister of El Niño. El Niño is, after all, the Christ child. And when an El Niño event occurs, this system tips in terms of the wind, but the water temperatures also change. You can perhaps imagine it simply like this warm water bubble, which is actually a dome. The sea surface is a bit higher there. It sloshes towards South America. Also because the easterly winds weaken, so the pressure of the wind subsides. And so we suddenly have 30 degrees instead of 23 degrees water temperature off the North American coast. That's a huge difference. By the way, the Galapagos Islands right on the equator are also affected because we know that above 26.5 degrees, the possibility exists to create very high-reaching tropical thunderstorms. Before that, the water is too cold, and then it becomes warm enough. And with that, the thunderstorms that are normally in the west can suddenly start off South America and also bring flooding there.
Yes, I find that totally fascinating, this change between the two phases, and that we see it in a certain rhythm. I definitely want to learn more about that rhythm in a moment. But maybe let's address the elephant in the room first. Now all the media are headlining a Super El Niño. I don't know, I've really read headlines there that almost make you feel afraid. What is that supposed to be? I realized that it's not a scientific term. Is that even a valid term? What is it supposed to mean, Super El Niño?
Yes, exactly. Well, actually, to be honest, there was a single scientific publication a few years ago in which American authors used this term Super El Niño, so to speak, or rather published it. But we in the scientific community don't use it. We speak much more of a strong or very strong El Niño, and we measure that based on the, so to speak, anomalies, the deviation of water temperatures in the Central Pacific. We have a large region there. And if the water temperatures there deviate more than 2 degrees from the norm, then we have a strong El Niño, and then 2.5 degrees, very strong. That varies a bit depending on the center, but that's basically the idea. And yes, indeed, our prediction models, there are various approaches, say, when looking across all predictions, now with a more than 50% probability, a strong but not very strong El Nino is predicted. That means one actually has to prepare for the fact that this El Nino could turn out to be strong. We can perhaps also discuss in a moment that there are major uncertainties there. But that's where the term super or mega El Nino, which is going through the media, comes from. Let me just briefly make one last point about that. Such a strong El Nino doesn't mean everywhere that there will also be strong impacts. Yes, so there's another uncertainty that comes on top of that. So in that respect, yes, there is possibly a strong El Nino, and especially those regions where this interaction with these water temperatures is very strong, they should already be thinking about what to do if this exact prediction should come true in the coming months.
I found a quote from you, which I think is also relatively current. I'll read it out. In the central tropical Pacific, the sea surface temperature anomalies averaged over the past weeks are around plus 0.5 degrees. Near the South American coast at about plus 1 degree. These current values are not yet considered record values. Now, I don't know exactly when the quote is from, but I think it's still relatively current.
Exactly.
But how do some media even come up with the Super El Nino if the data, well, are not yet record values, let's say?
You are actually talking about observations from around late March, early April. In the meantime, especially off South America, temperatures have increased even further above 1 degree. I can't give you the exact number. But the point is, first of all, El Nino is only just starting right now. Yes. And it reaches its peak, which is not always possible to say exactly in November, but perhaps also in January or March of next year, in any case, in the next winter of our hemisphere. And these Super El Nino terms refer to the predictions of the models. There are really dozens of them. There are statistical models, there are physical models. And as I said, there is a 50% probability of a strong El Nino. These deviations, that's why it also said in my quote, we would only expect them towards autumn.
I find it exciting that, you basically don't even know exactly when such an El Nino phase begins, let alone how strong it will be. So we have uncertainties everywhere in the whole thing, in principle. I think by now people are very sure that the El Nino phase is coming. But how can it be that I can be so sure about something regarding its basic occurrence, but the strength is still completely open? So how do I determine one? How do I determine the other?
Yes, that's a very good and really obvious question. I'd like to take a step back and ask, how is it even possible that we can predict this several months in advance? Because it is one of the few natural climate fluctuations on Earth where we are actually able to do that at all. And the point is simply this. Such a warming event is triggered randomly in the spring. It has to be in the spring by certain winds in the Western Pacific. Not every year, of course, but maybe every 2 to 7 years. That is how this periodicity, this quasi-periodicity comes about. And then these winds generate in the ocean waves in the mixed layer, but not surface waves. Rather, these are waves in the top 100 meters, which ultimately then travel very slowly through the ocean. And they actually take up to 2 months to reach the South American coast. Once they have been triggered, we can already predict that quite well for 2 months using the ocean models. These waves are then also reflected off that coast, and then they travel back again towards Australia. And that is also a relatively slow process. To put it simply for the layperson, we can hardly predict the atmosphere 14 days in advance. In the ocean, in the tropics, but it is in the tropics, such wave phenomena in the top 100 meters of the ocean can be predicted for several months. But then there is also a so-called prediction barrier, and that is in March. We also have problems with the models there as well. We are past that now, so that, well, by the way, we already see a clear warming signal now at a depth of 100 meters in the Western Pacific. And with that, we can be sure that an El Nino is coming, specifically with 82 to 90%. In principle, you could say, yes, you can count on it. But the amplitude is then again through strength, I should say, to make it more understandable, is then still influenced, so to speak, by the summer weather over the Pacific. And we cannot predict that. We don't know. It is simply not predictable. That means you can imagine it like this. We have the oceanic signal under control. But what then still affects the water temperatures and the teleconnections in the summer, we do not have that under control. And that leads to a great deal of uncertainty. In terms of the intensity, we will cross the threshold of 0.5 degrees in the Pacific. We are sure of that. But how far it goes beyond the threshold, other unpredictable weather and oceanic phenomena play a role.
In that respect, it is fascinating that we can predict the basic occurrence with such a high probability. That really is unusual in weather and climate research, meteorology, as you said.
Absolutely.
But there, 82% to 90%, I would say, let's assume it happens. You just said that it is usually only determined at the end of March in late spring. How does this, I think it's also called the spring barrier, come about? How does that happen?
Well, that's actually not quite so easy to explain. You just have to imagine it like this, perhaps. I'll try to use a simple image from physics that some people might be able to visualize. First, this system, we call it a coupled ocean-atmosphere system in the Pacific, has to be in a state where if I give it a little nudge, it then moves into another state. So I just imagine it like this. You have a ball, right, that you first have to push over a small hill before it really falls down into a next state, into a bowl, right? And this mountain, so to speak, is initially only low enough in the spring so that the atmosphere, the winds can get it rolling, right? And if you will, there are then a few nudges in January from the winds, and then in March, and then at some point we know the system has crossed over this point. It simply develops into this new state, yeah? But before that, we don't know how high the barrier is, whether this wind event is sufficient in terms of amplitude. So that's very, very difficult to explain. Weather and atmosphere are just a very chaotic system. But this predictability barrier exists, and only, so to speak, in April do we then know if the nudging was also enough to reach the new state.
Yes, I think that's a nice image. It makes sense too. I mean, everyone knows that from the weather forecast too. The 3-week forecast is of course less accurate than the 1-day forecast. Now, you had said that at a depth of 100 to 200 meters in the West Pacific, I believe, warming signals have been detected. That's already very deep. How do I even measure a warming signal at a depth of 200 meters in the ocean?
Yes, fortunately, that was a while ago after a, let's say, quite devastating El Niño in terms of its effects in 1982-83. The American Ocean Agency at the time, it's still the same one now, but back then decided we're building a measurement network of buoys in the Pacific, which still exists today, and will hopefully also survive the current conditions in America. You know what I'm referring to. And on these buoys, which are anchored, for example, every 10 degrees of longitude and then every 2.5 degrees north and south of the equator, they have a long anchor. There are also lines hanging from them. And on these lines hang sensors that measure temperature and salinity, among other things, and currents at various depths, yes. And this data actually allows us to see the signal and also to feed it into our model, so to speak. That's incredibly important. You're absolutely right, because we can't measure at this depth from a satellite. We can't see into it. It's actually these anchored buoys. This measurement system is called Triton, if you want to look it up, and it helps us detect an El Niño early in the ocean.
It's totally fascinating that this was installed there and that it now reliably provides this data every single time. Is there anything like this in any other ocean region? Or is this region so essential because of El Niño that it's only been done there?
Well, there's a very small network in the Atlantic as well, because there's even an Atlantic Niño, which is less common. It also happens in the northern summer and not in the northern winter. It then leads to warming of the water off the coast of tropical West Africa, like Angola and Gabon. And French oceanographers have also installed a much smaller anchored network there. The dynamics are actually quite similar, but it's not comparable to the Pacific West network.
Now, you also mentioned that one uncertainty factor is, if I understood correctly, the thunderstorm activity over the Western Pacific. How can thunderstorms help determine how the El Niño phase develops? Or is it just an indicator of something else?
No, well, that's one factor I mentioned as an example. That's correct. You have to imagine a thunderstorm, first an individual storm cell, leads to updrafts in the cloud via instabilities. And because of that, air naturally flows in from the sides, from the ground under the cloud. You could say it's literally sucked upwards. And over the Western Pacific, there are, of course, hundreds of very intense tropical thunderstorms. And these processes drive this entire circulation, gradually converging down at the bottom and then outflowing again at the top. The energy comes from the condensation of water vapor over the tropical ocean within the clouds. And this triggers what we call a Walker cell. This Walker cell normally has an ascending branch over the Western Pacific and a descending branch over the Eastern Pacific. Over the Western Pacific, we have storms. Over the Eastern Pacific, it's high pressure and it's clear. And then during El Niño, this storm zone and thus also this cell shifts towards South America. And how far it gets, how intense it is, this abnormal Walker cell naturally depends on this storm activity. And there are, of course, also other influencing factors besides just the local water temperatures.
Yeah, okay, good. So we now know how El Niño forms and what's currently happening. Maybe before we talk about the global impacts that this can have, one more question about the alternation between La Niña and El Niño phases and the overall cycle. It is a cycle after all, which means we have a certain regularity to it, but you can't predict exactly when what happens and how.
Exactly.
Now, the question would also be, what impact does human influence have on the sequence of these cycles? And I'll read a quote of yours again. Unfortunately, statements about the future frequency and intensity of El Niño and La Niña events are not yet sufficiently certain, which also means that a positive trend, as some studies show, cannot be ruled out. What can be said is, in the future, there will continue to be a sequence of El Niño and La Niña events of varying intensity. So we don't know anything for sure, more or less. But that there's some human influence, I think that's clear, but it can't be precisely quantified.
Exactly. Well, of course, with the quote you've picked out, you've said something that is true. We don't know for sure, so there's no consensus on how this will develop. Maybe later, when we get to the teleconnections, we can touch on it again. Of course, this seesaw will then take place at a higher energy level in the atmosphere and ocean, because the ocean is warming due to global warming, because the atmosphere is warming, yes. And that can, of course, even if the seesaw always has, so to speak, the same tipping heights in both directions, it can still mean something for the impacts. We'll get to that in a moment. The question one asks, however, is what influence does climate change have on El Niño? Does it mean, for example, will El Niño, the warmth, get stronger, or will they occur more frequently, or vice versa? Yes. And we in climate research don't agree on that with these models that still have certain shortcomings. That is to say, there are studies that say, yes, well, El Niño will get stronger, yes, but then others don't show that. And in climate research, it's always like this. If you were to say now, well, then let's just sit back and wait and see. You always have to give this little warning, well, that doesn't rule out that the group of models and people are right, that it will get stronger after all. Or put another way, in 40 years, someone will say, I heard that interview with Mr. Fink and Astro-Tim. He said it's happening and now we know it has become stronger. Well, there are certainly studies that show that. But communication to the public must be, we can't say for certain yet, so that it doesn't just stick in the media as El Niño is getting stronger. But again, water temperatures, especially in the Western Pacific, have risen. And of course, we already have more water vapor in the atmosphere in that region due to climate change. Yes. And then there's simply a larger energy reservoir available for this oscillation regarding the teleconnection. It has an impact on floods. It has an impact on droughts.
So you could perhaps say that El Niño itself might not necessarily become more frequent, but the consequences could be more severe.
Exactly.
Because of the teleconnection mentioned.
Exactly.
Is what's changing.
Exactly. That's it.
And is that because we have more moisture, more water vapor in the atmosphere these days? Or how could that be explained?
Well, there's this rule that for every +1 degree increase in global mean surface temperature, there's 7% more moisture. We call that the Clausius-Clapeyron relation because it's derived according to that equation. And you have to generally imagine it's exactly the same. If I may make this comparison as with hurricanes or tropical cyclones, typhoons, they simply find a larger reservoir of moisture. And ultimately, there are mechanisms that bring this moisture to the ground as rain or heavy rain. Yes, the moisture as a reservoir doesn't just rain. You need a trigger, you need a catalyst. And in the same way, this El Niño oscillation finds significantly more water vapor, which means we're the teleconnection means more rain. We can also assume that it simply rains much more intensely because more is available.
Well, let's stick with these teleconnections because that's what El Nino is famous for, that people say, oh, El Nino has occurred, and suddenly, to exaggerate, there's a drought in Africa. Or then suddenly the hurricane season, it changes. How can that be explained at all? And why do we have such great uncertainties here too? I just read that, for example, in 1998, a major drought was predicted in Africa, but for instance, that didn't happen at all.
Yes, exactly. Well, first of all, El Nino actually has an effect all the way around the globe in the tropics. And that's due to this Walker cell system that winds around these tropics. So with ascending branches where there's a lot of thunderstorm activity, then there are either easterly or westerly winds at high altitude, the outflow, and then they descend. And this whole cell system is shifted, or sometimes the branches strengthen or weaken. So that's the mechanism of the teleconnection. This so-called Walker cell in the middle latitudes where we live, it's actually almost exclusively the countries bordering the Pacific that feel something as far as, let's say, regions like Florida and maybe Venezuela. But beyond that, Europe, Asia is simply too far away. So, and then of course, it's also the case that the further you go from the original signal, the more other mechanisms will modify it. That means the fairly certain impact is if we get these water temperatures over 26.5 degrees off South America. So there'll be enormous rain in the otherwise very dry northern Peruvian desert in Ecuador. Yes, we're actually pretty sure about that. And on the other side, in Australia, Indonesia, Northern Australia, to be more specific, it will be drier there. And those are statements that I would already plan on as a decision maker. Especially if I'm a farmer, I would consider what I'm growing, more drought-resistant crops, or I'd prepare for flooding. So then there's another relatively certain impact. I'm not talking about Southern Africa now, but about the Horn of Africa, so Kenya. They can expect more rain in January. If I look at Southern Africa now, where we also do research, by the way, then that example from 97, 98 is a good one. Because a pattern of water temperatures in the Indian Ocean apparently neutralized that signal coming from the Pacific, to put it simply, right? And this thing, because these events aren't that frequent, we hadn't seen it in the past, it wasn't really on our radar. But today we know, yes, for, let's say, Southern Africa, the probability of a drought in the next rainy season, next winter, is high. But it can also lead to these false predictions that we just can't accurately estimate. And as a decision maker, you always have to ask, if I do something now, will it cost me a lot? Or is it very expensive if it actually happens? It's a difficult trade-off. Nevertheless, I know that in Southern Africa, even now, in the relevant organizations, farmers are being informed that it could be drier. But as I said, there are regions where El Nino leads to the, let's say, well-known effects with greater certainty. And there are other regions where we now know, yes, it can also go differently. By the way, one very well-known region is California, where during a strong El Nino a few years ago, there were actually floods instead of drought. So because of that, you always have to be a little bit careful. El Nino forecasting has its uncertainties. And for some regions, the impacts are then fraught with even more additional uncertainty. And the key is then to know how reliable the forecasts were in the past and then to react accordingly.
Yeah, I mean, that's the only way responsible preparation can look, by working with probabilities. There's always that group of people who, when a forecast doesn't come true, feel somehow vindicated. Like, oh, the scientists can calculate whatever they want, it didn't happen. Nothing is 100% certain, right? The universe could disintegrate in the next second, but you can only work with probabilities.
Yes, exactly. That's the point. That's generally what we meteorologists, since I also work a lot in forecasting, are naturally always confronted with. It's a difficult concept, even in science and for scientists, and for the layperson even more so, but still, everyone already works with certain probabilities when deciding whether or not to take an umbrella. And in the end, I'll say it again, it's a relatively simple rule. If the probability is high, but my costs, if it happens, are low, then I might choose to do nothing. If I lose my life or face huge costs, then I might act even at a lower probability, but then I have to accept those false alarms. That's just how it is.
I think the net benefit is clear regarding this research on the early warning systems that were installed there. I think that's beyond question. Now, you said in Europe now we are very far away from the Pacific. You can't really name any direct consequences, at most indirect ones, I assume. And that's probably more what's relevant for Europe, that we might then also be affected because of crop failures in other parts of the world. But we don't really see direct meteorological effects on Europe, do we?
Yes, exactly. But I'd still like to clarify that a bit more. There are, of course, studies in the media that say, yes, we find a weak but statistically significant correlation to slightly milder winters, which, by the way, have become more likely in Europe anyway due to climate change, and to more precipitation in spring in the Western Mediterranean and Morocco. But to be honest, that's really such a small, what we call explained variance, that one shouldn't go out and say these effects will happen. That's why most experts, myself included, say, no, we can't say anything about that here now, which doesn't rule out a causal chain occurring in an individual event. But I wouldn't count on anything at the moment.
Now, another meteorological topic, let's say, that often makes it into the media is the Gulf Stream and AMOC, the Atlantic Meridional Overturning Circulation. Is there any connection to tropical meteorology, as I'll just call it, where you can say there are some interactions? If we have a super strong El Nino now, will that affect the overturning circulation, or is it completely independent?
Well, largely independent. An El Nino it's also a completely different time scale, this overturning. So that's many years, decades, several decades. And El Nino is much too, if you will, fast to trigger reactions there. We know that there were decades from the beginning to the middle of the last century when an El Nino tended to be linked to slightly colder water temperatures in the Atlantic. But that hasn't been the case in recent decades. We also know, by the way, that it's often in the Indian Ocean, which is more relevant and also happens much more frequently statistically, that there's a pole of water temperatures called the Indian Ocean Dipole, which then also tends to lead to warmer temperatures in the Western Indian Ocean, actually, and cooler in the Eastern Indian Ocean. But there are also independent fluctuations there, just like with the AMOC. So in that respect, regarding the Atlantic AMOC, in other oceans like the Indian Ocean, we actually see the triggering of a dipole during some El Nino events.
Yeah, the more you learn about it, the clearer it becomes that it's just an interplay of incredibly complex systems. I find it all the more amazing that we can even make these predictions at all. In recent years, because we're working with such complex systems here, has the progress in the field of AI actually changed anything for you? Does it make the prediction easier?
Well, the answer is a clear yes, both in classical weather forecasting, where AI can predict some phenomena better than the models. And there, even if I haven't come across a paper recently, I also expect that El Nino forecasting can become more accurate. A bit of a problem, of course, is that AI needs a lot of training data. Now, you have to imagine, well, we've only really had good atmospheric reanalyses since 1979, since geostationary satellites have existed. So let's say 55 years maybe. Then you can imagine how many El Nino events there were if it occurs every 2 to 7 years. So, well, under 10, right? And then the question is how to train an AI, whereas with weather forecasting, we have hourly data over 50 years, so that was possible. Nevertheless, these statistical models already exist. Standard procedures have always assumed a certain linearity of the events, so to speak. And AI is particularly capable of better reflecting these non-linearities that we simply have in the climate system. And therefore, I expect that AI predictions will actually reach at least the quality of numerical models, which are very complex despite this training issue, and hopefully also provide better answers for some of the teleconnections as well. I'd like to give you a very classic example from another field. So in 2018, there was an article by a famous hurricane researcher in the US. And he said that with our forecasting system, we've already achieved what's theoretically possible. The prediction quality, so to speak, is optimal. It can't get any better. And he was referring to the paths of these storms. Well, AI improved that by another 30%. Not the intensity prediction, that doesn't work, but the path prediction does. And so I simply believe in the tendency to be able to predict that we'll see improvements in this forecast too in the next 2 or 3 years, and especially regarding the teleconnections, because there's still quite a bit of uncertainty there. And that will also give us better possibilities. And let me say one more thing. El Nino is just so strong. It's a predictable system, and in many countries, our forecasting has already helped to significantly improve food security in the tropics, for example. And I think that's a really great thing, even as a meteorologist, that you can really do some good with your forecasts, or as an oceanographer. Just a small side note, there's the food, the agricultural exchange, the largest in the world in Chicago. They price that in, don't they? So they have these, there are people who look at our forecasts, and then on the exchange, they're already betting and wagering on future prices, if you will. That's also very important in the financial world.
Yeah. A friend of mine is a coffee roaster, and he also mentioned, I don't even remember now in which direction, but that the El Nino news had already influenced raw coffee prices.
Yes.
Yeah, absolutely. So I think, as I said, the positive benefit is undisputed, and it's also nice to hear that in the future, AI might have an all-around positive benefit if we can better determine the teleconnections. When you're confronted with AI in everyday life now and see some bad AI videos on Instagram, you sometimes doubt the positive benefit. But I think that's a very nice example.
Yeah.
Well, then maybe to wrap up, because I've already stolen almost 40 minutes of your time, the question is, what exciting research projects do you have going on besides El Nino? I believe your research group at the Karlsruhe Institute of Technology is the Tropical Meteorology Working Group, right?
Yes, that's correct.
What else is happening there? What exciting things are you currently researching besides El Nino?
Yes, well, actually, it also has something to do with forecasting. And we call it, I'll explain what that is in a moment, improved subseasonal forecasts for Africa and, by the way, Vietnam. So that's the objective. And there we're actually not trying to predict the next few months, because those are the so-called seasonal forecasts. We were just talking about that, weren't we? But you don't predict a single day there, just a monthly average. Instead, we try to predict averages for temperature, but also accumulated precipitation up to 6 weeks in advance. And we're trying to find out where that works, under what conditions it works, and how AI can be used to recalibrate these forecasts so that they do have value after all. Specifically, for example, in Africa, farmers are incredibly interested, and of course the states, in predicting the start of the rainy season. And the earlier you can say that with, so to speak, good certainty, the better. Dam managers also want to know, how do I manage my dam? How much water can I release so that I don't run into a problem? That means we're trying to close what we call a forecast gap between the classic 1 to 2 week forecasts and these monthly forecasts. And I'd also like to say again, why is that such a gap? Well, in classic weather forecasting, you determine the initial state of the atmosphere. You then have information about that initial state. Then you take models that aren't quite perfect and try to integrate them into the future, usually for 2 weeks. And with each passing day, you basically lose predictability. The information from the initial state is lost because the models aren't perfect. So with El Nino, we just talked about it, so it fits in well. The ocean comes in and brings this predictability back into the atmosphere after 2 or 3 months again. In the tropics, the atmosphere is coupled to the ocean. So in between, let's say between 2 and 6 weeks, the question is, the initial conditions no longer count and the ocean isn't really in yet. How can we? And there are a few phenomena that do it after all. So we're really trying to squeeze out every last bit of predictability. Initial results show that in East Africa, for example, you can still make predictions in week 4, but no longer in weeks 5 and 6 for total precipitation. In other regions, unfortunately, it's already over by week 3. Yes, and so that's what we're trying here. And there's new data available, which is freely accessible. Anyone can use it, every citizen. From the European Center for Medium-Range Weather Forecasts, they run their model 100 times every day. That's 100 members worldwide for 46 days in advance. We download that data and then we see if it can be used.
Incredible. Yes, I find it so exciting about your job that it's also such a global matter, so to speak. It's about things happening in East Africa, in West Africa, in Vietnam, in the Indian Ocean, in the Pacific. It's just amazing. It's just amazing. Does your daily work involve a lot of business travel, so to speak? Or can you basically do it all from your little office in Karlsruhe?
No, we actually do field research on site as well. I'm very grateful for that. It's a privilege to be able to do that. And let's put it this way, I actually come from weather observation, from weather forecasting and working with people in the field. Experiencing the local weather firsthand is not just motivation, but also inspiration. And yes, I've been able to experience many places in Africa and also in Vietnam, which in the end also means that you get to meet the people there. And maybe a bit differently than a tourist. I don't mean that negatively, but you get a bit more into the societies, and that's a real privilege.
Yes, absolutely. Yes, so that's a very nice closing statement. Great. I found it very, very exciting again. This is already our second conversation. If we manage to do it again in 2 years, we'll have already made a tradition out of it. But in 2 years, we probably won't have a new switch between El Nino and La Nina yet. We'll see. Yes, so as always, a lot of comments will probably come in. If you have the time, feel free to take a look. Let's see. Last time, over 180,000 people watched our conversation. That's really incredible. Let's see how many it'll be this time. So thank you very, very much, Professor Fink. And until next time.
Until next time. Yeah, yep.
Yeah, I hope you enjoyed the conversation with Professor Fink as much as I did. If you have any questions for him, feel free to write them in the comments. And to make sure you don't miss any more expert talks, remember to subscribe to the channel now. And also give it a thumbs up so we can hit the 5,000 likes mark. The algorithm loves that. And now we're traveling to another exciting region, Siberia. In Russia, giant craters are suddenly appearing. Some over 100 meters deep, they appear out of nowhere, releasing something from the permafrost that could be very dangerous for us. What's behind it and what it means for the future, we'll explain in the video linked in the top right. Be sure to check it out, it's very exciting. And if you'd like one of the galactic Astro-Tim shirts from the videos, plush planets, or my signed books, you can just click bottom left and browse the space shop. Every order really supports my work. Otherwise, I'd say I'll see you in the next video. Take care, guys.